And I put a subtitle here, slightly different to the one in the abstract, but it says exploration pitfall or excuse. And the rationale behind that is that in many parts of the world, I think residual gas is probably less common than it is in Trinidad. And it's often used as a reason for failure. When wells are drilled on DHI anomalies and they don't come in, the geophysicist, and I'm a geophysicist, so I know this, the geophysicist excuse is often that, oh, it was fizz gas. You know, we did our best, honest. It's just it was fizz gas, and you can't tell the difference between fizz gas and real gas. But actually, you know, many areas fizz gas isn't that common, and the reasons for failure are other than the presence of fizz gas. But in the Columbus Basin, I think this area is actually an exception. And I think the answer to this question here, I think, is that residual gas anomalies in the Columbus Basin are a real hazard, a real pitfall, and there are a lot of them around, and it's probably the main reason for failure for wells that are drilled on good quality DHIs. And I hope this talk will persuade you that it is a high risk feature here. But there are subtle clues which sometimes can at least help you risk the anomalies accordingly. There's no magic bullet yet to tell you this is definitively low residual gas or definitively hydrocarbons, but maybe there are subtle hints in the data which can help you distinguish the two. So if we go on to the next slide. The first thing I should do is acknowledge quite a lot of, a good many people have worked on this in the past from within BP in Trinidad and Tobago. There are too many individuals really to cover here, but there are some particularly that I want to highlight. People like Wes Phillips, who's left the company now, but is still actively working on things like Trinidad. Jonas Bailey, Gillian Kirby, Christian Elligan, Ed Shaw, Rob Elliott, Crystal, who's here in the audience today. She's one of our final year interns who's done a lot of useful work analyzing amplitude anomalies in the Columbus Basin. And he also uses material from the leading edge, a publication in 2000 by M. Batzel and De Guar Han. I'm not sure if I pronounced his name correctly, but there's material in there. Yeah. Okay, next slide, please. Okay, what I'm going to do is take you through, firstly, some definitions on residual gas and fizz gas. These terms are often used interchangeably, and I think that's the reason for a lot of the confusion around the whole nature of residual gas. There was an email chain sent around in BP about a year back, just on the significance of fizz gas. And the responses that came back in this email chain ranged from never seen the stuff, don't believe it exists, to yeah, it's a nightmare, it really plagues my exploration efforts. So there's quite a wide range of responses, and I think that's partly because we can be very loose about our definitions on exactly what we're talking about. So I'll just go through some definitions of these things before getting into the body of the talk. I'll also just say a few words on why it is important, just showing some statistics from the Columbus Basin and some examples of successes and failures, just to give you a feeling for why this is important here, just in case you're not already convinced. Then a few words on how we think these low saturation gas accumulations form, because again, there's quite a lot of confusion about how these things actually form, how they occur in the first place. And then I'll get onto the meat of the talk and give you some examples of what we consider to be residual gas anomalies. Some of these are tested by the bit and proven, others are interpretive. So there's a mixture there. You can feel free to disagree with me on the interpretive ones, but I think they're often very good clues as to what's residual and what isn't. And then, having seen the examples, I'll try to summarize on some characteristics of the residual gas anomalies, which hopefully will give you some chance to maybe recognize some selected ones in the future. So we go on to the next slide, please. Okay, some definitions then, at least definitions that I use, one or two other people use. I don't know if these are widely accepted yet, but these are suggested definitions, if you like. So residual gas, when we talk about that, we're talking about low gas saturations, and these range typically from 10 to 30%, left behind when paleoaccumulations have leaked. So it's an indication that there was an accumulation there. It's leaked out, the gas has leaked out, and it's left residual gas behind. Fizz gas, and here I quote from the leading edge, is an ill-defined and misapplied concept. Now, sometimes this is applied to all low saturation gas zones, including residual gas. Sometimes it's applied to gas exsolved from solution. So like the gin and Sprite that I had just before standing up here, there was gas exsolving from solution in that. The issue with gas coming out of solution is that gas solubility in water is very low. The solubility of methane, even of carbon dioxide, is relatively low in water. So the saturations that you get, the saturations that you can theoretically get from gas exsolving from solution are typically relatively low saturation, around about maybe 5% gas saturations. Certainly as you go deeper, below 10,000 feet. But even in the shallow part of the section, this, volumetrically is difficult to get up to the same sort of saturations that the residual gas will give you by getting gas coming out of solution. And sometimes this term is even applied to formation water saturated with solution gas, which doesn't have any free gas in it. The view being that maybe gas at its water at its bubble point will be more compressible and will give a difference of seismic response. So sometimes that's called fizz water rather than fizz gas, where you get 0% free gas, but the water's at its bubble point. This terminology causes a lot of confusion. And what we should do, and here I must admit that I suspect somewhere in this slide set I'm actually going to break my rule here, but here I've suggested that we cease using this except for the very rare occasions when we are really talking about exsolved gas. That for the other cases where we're not talking about exsolved gas, we should refer to it as residual gas. But I know buried in here there is a slide with fizz gas on it. It's not one of mine, it's one I've got from somebody else, and I didn't edit it, so I'm kicking myself now. But anyway, residual gas is what we're talking about. Fizz gas is I'm sure, much rarer and much less significant in the seismic world. So in either of these cases, the gas can either be biogenic or thermogenic. The rocks don't really care about the origin, but it just so happens that I think residual gas anomalies in Trinidad are likely more, most of the time, are more a result of biogenic gas. These saturations, I'll just come on to some evidence behind why we think residual gas saturations can be of the range of 10 to 30%. If you want to know more about the fizz gas saturations, then I'll refer you to this paper in the leading edge in April 2002 on this concept. But the main thing I want to do is differentiate residual gas saturations from residual gas concentrations from fizz gas, and I'll show you the evidence that supports this saturation range. On to the next slide. Okay, this is one of the few graphs that you'll actually see in here. I'm not going to go through the theory. I apologize if you came here hoping for page after page of equations and graphs. You have an interpreter talking to you, so it's going to be very much more, seismic sections and pictorial displays rather than graphs and mathematics. But the chart on the left here is typically the one which is used to explain why fizz gas or low gas saturations are a nuisance, why they're a problem. And effectively what we're looking at is water saturation along the bottom, or if you like the inverse of that is gas saturation. So you have low gas saturations on the right, 100% gas saturation on the left, and it's the impact of varying gas saturations in a porous rock. So what it shows is that you have a big impact on compressional impedance and Poisson's ratio with a relatively few percent of gas saturation. This is taken from Depois and Hang's paper on this. So with a few percent of gas saturation, you have a big impact on the rock properties. That's certainly true at shallow depths. What they were arguing is as you go deeper, that effect becomes much more gradational, and you have much more gradational response, and that low gas saturations of the order of a few percent don't have much of an impact. So if you tamp down, I've got just some animation on this slide. Okay, so fizz gas, fizz water then would occupy this portion of the graph, and they were debunking the idea that certainly in the deep water Gulf of Mexico that it could be the cause for anomalies. So if you've only got less than 5%, it's not going to have a big impact given this sort of response. Even up shallow, it has, it doesn't have a full impact, and the depths transitional between these two would have, again, a relatively muted impact. But if we look at where the residual gas anomalies typically sit, they're down on the flat part of these curves, clearly down. You're getting virtually all the hydrocarbon response, the gas response from these saturations. You don't need to go up to the 100%. And even at great depths, theoretically, you're still getting quite a big response from the residual gas saturations. Certainly sort of more than halfway towards where the full saturations would sit. So if you keep tabbing down, it's just the effect of gas pay with full saturations. Not much difference from residual gas up shallow, and even at great depths, there's still quite a lot of similarity between these two, and radically different from the fizz gas case. The reason for the different response at great depth is that basically, as you compress the gas, it becomes less elastic. It stops behaving, if you like, it stops behaving quite like a gas and more like something halfway towards a liquid. It becomes less compressible. So as you go deeper, the response gets less. So their paper, which was debunking the excuse, if you like, for failed DHIs on the basis of low saturation gas, was really aimed at the wrong target. Their logic was impeccable when it comes to fizz gas saturations in here, but doesn't really work when we're talking about residual gas anomalies. So residual gas, theoretically, should be a problem, and in practice, it most certainly is a problem. So we go down to the next slide. These are the slides I was talking about, justifying the gas saturations I'm quoting for residual gas. So this is just from core studies looking at residual gas saturations. You take a sample of core from the reservoir, and typically when you flood it, you're still left with residual gas saturations of averaging just over 20%, but ranging from about 10 almost up to 40%. So residual gas is volumetrically very significant, unlike the sort of fizz gas situation that we're talking about. So that's from core. If we go down to the next slide, this is just some log calculations from one of our wells. There are clearly two gas pays in this well, looking at the resistivity spikes here. If we look at this lower one, there's a clear gas pay, gas-water contact. But if you look at the sonic log in blue, it kicks back through the gas zone. It stays back some distance before kicking positive again at this point down here. This is a paleo contact. This is where the residual gas comes down to. It's also very apparent on the Poisson's ratio log. So P-wave velocities are seeing that gas effect. They're not distinguishing low saturation gas, as in this zone here, calculated at 20%, from the overlying sort of more or less fully saturated, 80% saturated reservoir. So the log analysis here is supporting that number of around about 20% for residual gas accumulations. So that's the logic behind when I say it's a range of sort of 10 to 30% typically for residual gas. If we go on to the next slide. So why am I up here talking about residual gas? Why do I think it's important? Well, it's largely in the Columbus Basin. BP's history is largely one of drilling DHI anomalies, drilling them out and finding a lot of gas as a result. We often find a lot of gas which doesn't have DHI anomalies. Crystal can probably talk to that more powerfully than I can at the moment. But a lot of gas is masked. But basically, if you drill on structures with DHI anomalies, you end up with a very high success record. You just tend to find quite a lot of masked gas at the same time. But exploration targeted at DHIs has really been BP's story in the Columbus plain. However, not all of them are successful. Even some attractive DHIs still fail, and I've put a range, 15 to 25% in there. It's difficult to pin it down to a single number, but there is a significant failure rate even with very attractive DHIs. It's a low failure rate, but it's still significant. So these things, some of them may look like slam dunks, but still let you down. And the vast majority of those failures in the Columbus Basin, we believe, are due to the presence of residual gas. Now that's very true for the Columbus Basin. If you go to other parts of the world, that's probably less true. There are other reasons for failure in many other basins, and some of those may be more likely than residual gas. But in the Columbus Basin, failed DHIs, I think, are almost always due to residual gas. Okay, this is one of Crystal's slides that I stole. This is a success case example. So these are the sort of things that we've been drilling in the Columbus Basin with a high level of success. So what it shows is an amplitude map, bright amplitudes in reds and yellows, superimposed on the structure map. You can just about make out the structure contours in the background, one of which has been highlighted in red. So this is a beautiful example of a success case drilling on a DHI. Good conformance with structure. The seismic section shows a nice bright amplitude anomaly and a flat spot underneath. So if everything looked like this, we'd be in heaven. We'd drill them all out, but we'd still get a 15 to 25% failure rate. If you go on to the next slide, there's maybe a more typical example, another success case example. But here, although the amplitudes are concentrated within the structure, there are amplitudes streaming off down towards the south on this particular feature. And the amplitudes towards the north tail off before you get to the structural closure. This is more common for a DHI example in the Columbus Basin. Half of the prospect, or a significant prospect of the portion of the prospect, is masked by shallow gas. So the amplitudes are tailing off towards the north side, and the streaming amplitudes off on one flank are often problem. So seeing good conformance with structure can be a problem. You often get these higher amplitudes on one flank of the prospect. And we'll see some examples later on which maybe explain why you get some of those. I think in some cases it's an indication that the accumulation was more extensive previously and has been tilted or shrunk, and what you're seeing is some residual gas left behind along the way. But anyway, that's another success case from the Columbus Basin. I think if you tab down, I think we get to a failure case. This is just a nice, bright seismic response sitting in space here, but a very abrupt termination to the end of it. As you can see from the well logs going down through this, gamma is the black curve, and the resistivity is another black curve on the right. There's no resistivity response to this at all. There are other water-wet sands above and below with no amplitude response. This one's got a bright amplitude response but no resistivity response. It's almost certainly due to residual gas in here. That's why this thing glows in the dark. So it's a failure case from Trinidad. I think the next slide just demonstrates that the point I was making a bit earlier, that in other parts of the world you get very convincing failure cases. It's a beautiful flat spot here going across this structure. It's got nothing to do with residual gas. It's in the middle of a shale section, and this is actually a diagenetic flat spot going from probably from opal sea to quartz, and this is off Greenland. So don't necessarily, look at DHIs and only think in terms of residual gas as reasons for failure. There are other reasons why they can fail, and particularly, if and when you get posted to other parts of the world, bear in mind these other pitfalls. Okay, this is just some statistics to demonstrate why residual gas is such a headache for us. This is statistics compiled over a period of time, initially by Wes Phillips. I've just brought them more recently up to date. And what we're looking at here is penetrations of sands. They're not always primary targets for wells, but they're just sand penetrations. In total, nearly 400 sand penetrations in the Columbus Basin. And we've subdivided those into penetrations which are on structure, and generally we like to drill on structure, so most of them are on structure. But there are a few off structure, and in general that's where, for instance, if we're drilling on a tilted fault block, you may be within closure at some levels, but at other levels you'll drift out of closure. So we've separated them into on structure and off structure. We've subdivided them according to whether they got pay or no pay, and we've also split them up according to whether they had strong amplitude response, weak amplitudes, or no amplitudes. Now the graph on the left just shows total number of cases. On the right it's normalized to a percentage view of the world. So what this shows is that off structure, unsurprisingly, we haven't found any pay at all. They're all failure cases, so good message there. Always try to drill on structure. In the cases on structure, where we've drilled on structure and we've got a strong amplitude response with conformance with structure, we end up with a very high success rate of getting close to 80% success rate, where there's a weak response, but still an amplitude response, but even if it's weak, you get close to 75%. The reason why I think there's also a reasonable success rate on the ones with no amplitude on structure is that a lot of these are actually masked by these other anomalies. So if you drill at some point on a structure with amplitudes, then you're likely to find some pay which has no amplitude response. It's just been masked by the overlying stuff. So very high success rate, but the failure cases up here, if you tap down, please. Failure cases up here are most probably due to the presence of residual gas. So it's something, if we can understand these failure cases, then maybe we can eliminate some of these dry wells that we drill. Tap down again, and again. What I've done here is just simply subdivide the previous graph into depth ranges, and it shows that the failure cases are actually that they get more likely as you come shallower in the section. So we're more successful with deep DHI anomalies than we are with shallow ones, and I think that is telling us something about the prevalence of residual gas anomalies, that they're actually more common in the shallow part of the section, and probably brighter and more alluring in the shallow part of the section. So next slide, please. So just a few words then on how these are formed. This may be stating the obvious, but we still sometimes seem to get some misconceptions around them. So residual gas, I'm hypothesizing, always starts with a paleoaccumulation. If you tap down again, and then maybe you'll tilt that, keep tapping down. If you tilt it, you can leak some out and leave a residual gas sort of scar or tail behind, but still have a valid gas trap above it with proper saturations above it. Tap down again, please. Another route, tap down again, would be to take your paleoaccumulation and bury it, so you compact the gas, and then you may be left with high gas saturations at the crest, but a residual gas tail. Or the other obvious route, if you tap down one more time, is maybe the trap just leaks. You might have renewed movement on the fault, or you may breach the overlying seal and leak off some of the gas, and you end up with a trap which is entirely filled with residual gas. The one where they don't form, if you tap down, is that it's physically not possible to actually fill an accumulation with residual gas saturations. It's like trying to fill your bath with low saturation water. It just doesn't work. These things fill, the hydrocarbons migrating into them will migrate until they reach the barrier, until they reach the trap, and form a proper accumulation with full gas saturations, and then build downwards. You cannot fill a trap with residual gas. So that's, you know, if migration is a problem, you will have partially filled traps, but they will be filled with high saturation gas. You cannot generate a residual gas anomaly without actually having a high saturation gas zone there in the first place, which then subsequently leaks. So now it's time to get onto some real examples, and this is just to show that the examples I've picked are actually fairly widespread across BP's acreage here. They're all on BP's acreage, all the examples I'm showing, but there's a mixture from the sort of western areas and also from our gas province in the east. So, next slide, please. Yeah. So this particular example, this is one of some DHIs which are maybe just a little bit too good to be true. There's a structure here with some very bright amplitude anomalies on the flanks, which terminate very abruptly down dip. So it looks as if you could have, you know, a very large trap here on the flanks of this structure. But when you look at the amount of relief, there's over a second of relief on some of these anomalies, and the crest of them is within sort of 600 milliseconds of the seabed. That should flash warning signs. These columns are just too big to be supported by that amount of rock. So first warning sign is that these just look too good to be true, too big to be true. In a map sense, again, high amplitudes here are shown by the reds and yellows. The seismic section that we're looking at is running north-south through here, down dip from the crest of this ridge up in this area. In a map sense, the down dip conformance with structure isn't very good. Although if you were a wishful thinker, maybe you could pick out local areas where it conforms with structure, and then have sort of stratigraphic edges and other things. You know, maybe velocity anomalies in here to help you argue away that particular down dip edge. But you'd also have to argue away the lateral edges. You'd need stratigraphic trapping, you know, an extensive stratigraphic trap on the flank, and you'd also need one on the other flank over here, because it can close within structure. So there are several warning flags there, if you like. You need quite special pleading on the trap. The final element is that there are here on the crest of the structure, there's some very nice amplitude anomalies and flat spots. So to have these ones down dip from it, you'd actually have to have a stratigraphic trap to separate off, you know, sands like this from the up dip accumulations as well. So you'd also need some form of stratigraphic trapping through here to have this large accumulation. Now this isn't just, you know, something I've pulled up as a sort of deliberate red herring. This was actually a lead in our prospect inventory, which was in volumetric terms looked highly significant, and it took quite a while to kill this one off, because I think it is a classic residual gas anomaly. And I think what's happened is, if you have a look at this structure, you can see that a lot of this, a lot of the tilting here, a lot of the structure is very recent. Began to form at about this time, and persisted for, you know, there was a period where the structure was growing. But it's relatively recent. There's been a lot of recent tilting on here. So I think what happened was that this was charged at an early stage when the structure was much broader and gentler, before this tight fold had formed. And then the rocks were subsequently folded, and the gas leaked up dip, formed these crestal accumulations, but couldn't support these long columns and blew from the crest. So I think if you tap down, there's just a sort of summary of that point here. So the diagnostic features from this anomaly are that, you know, the column height was unrealistic for a valid hydrocarbon trap, and the conformance with present-day structure wasn't too good. And in order to make the trap model work, there was quite a lot of special pleading. So as one of the interpreters in BP likes to point out, it fails the principle of least astonishment. If you're given two models, either this being a residual gas anomaly, or you have this amazing trap with stratigraphic edges above and on both flanks, and an exceptionally good seal to hold back these column heights, then one of those explanations is much less astonishing than the other. And I think the residual gas explanation is much less astonishing here. And as I say, I think it was charged soon after the reservoirs were deposited, when the paleo trap was broad and gentle, and subsequently it's been folded into a much tighter structure, and the seal is blown. So we're going down, looking at some other anomalies. Okay, this is an example of one that probably conforms to a paleo structure. Again, a very nice, bright amplitude anomaly here. This is actually a failure case that I used a moment ago. Tab down one more time. This is the seismic section through it. This is that north-south line. Very nice down dip edge to it here. So if it didn't have a well in it, it looked quite convincing. But actually, if you look at the structure map, this edge, you can maybe just about make out, it's the same scale as this map here, you can make out where that edge goes, and it doesn't conform at all with the present day structure. It swings across it quite radically. But if instead of looking at the present day structure, you take a line, this is a dip line down that structural nose, and I've just flattened it on a shallower reflection event. You can see the seabed up here, it's a very shallow anomaly that we're looking at. That's the seabed, which should actually be flat, but I flattened it on one of the events which is dipping above the amplitude anomaly. All these reflections would have been deposited horizontally initially. We're in a deltaic setting. All these, as flat spots tend to do, it's not flat. It sags, partly because of gas from within the reservoir zone itself depressing the response. But in this case, there's also shallow gas higher up in the section, which is causing the sag on the gas spot, on the flat spot. Now, in this particular case, after it was drilled, there was quite a lot of excitement. The top reservoir was up here, there's a flat spot. Volumetrically, it looked pretty significant. It is actually quite significant, but it looked even bigger. But the problem is, you may be able to see that the flat spot is some way below the base of the gas column in here. So there's you've a relatively small gas column and then a flat spot sitting all the way down here. So the question is there a static shift that needs to be applied to the seismic data? Is the wavelet somehow distorted and really we need to bring all the wells down here to tie? Or is it our favorite bugbear, residual gas? And I suspect you know the answer. If you tap down, the slide goes black. The reason for that, sorry, my expertise with Strapworks is not as good as it should be. I should have got Cheryl to help me here. But the sonic logs are white, so the only way I can really make them stand out here is by making the rest of the slide a lot darker. But you'll see the sonic logs kicking back, go into the gas zone, but then swinging back out with a strong positive kick at this point here on the sonic log. Likewise over here, strong positive kick on the sonic log, well above the base of the sands. So this sonic response in here, effectively you're seeing a gas response below the base of the resistivity. So this is your residual gas zone below the base of the high resistivity peak. That's what's giving rise to the flat spot in here. So there's a risk that you could overestimate the size of these accumulations by not taking into account that residual gas zone at the sitting below. These three wells is in a different fault compartment within the same overall big structure. And it looks as if those different compartments at one stage in the past had all filled to a common level, but maybe since then they've all leaked at different rates. So the present day contact has shifted in each of the fault blocks, but the paleo contact is consistent and is flat across the three. So would you recognize that pre-drill? My guess is not. You're a better geoscientist than I am, if you would. If you tab down, in terms of pre-drill diagnostic features, there aren't really any. Again, it is a relatively shallow anomaly, and our statistics indicate that actually, these are higher risk, and rather than putting them at the 80% chance of success, what you should be risking it more conservatively. But that doesn't really tell you anything about these sort of cases where you have a partial accumulation. These risks are all about, is it going to work or is it going to fail? It doesn't really tell you, well, actually these anomalies may work, but they may only be half full. We don't really have detailed statistics on partial fill yet. In terms of post-drill, there are some obvious things here. The flat spot is deeper than the true contact. As soon as you produce synthetics, that will become obvious. The residual gas has a major impact on the sonic, but just a minor impact on the resistivity. The residual gas, is obvious in a post-drill sense. But the explanation here I've talked you through, effectively, we think it did once have a common contact across all three compartments, but now it doesn't. And that could either be due to static fill and spill. Maybe it filled to the constant level, then leaked and stopped leaking with the contacts frozen in different positions. Or maybe a lot of these accumulations are dynamic. Maybe they're continuously filling and spilling, and the rate of charge into the different segments might vary. Maybe there's a constant leakage rate, but you're actually charging some segments more than others. Either explanation would give you a stepped present-day contact. Okay, if we keep going, I think we've got one or two more examples. Okay, this is an example. Again, this one was quite fun. We had some quite heated internal arguments in BP about this anomaly. What we're looking at is these events here, nice bright events with quite a distinctive sort of flat termination to the down dip at this level. And the arguments are all about whether, you know, is there an accumulation like this, or is it actually a fair bit smaller? So this is a dip line across the anomaly. On a strike line, it also looks quite good. You get bright amplitude anomalies on the crest of this nose in here. But on a mapped sense, it looks a bit less convincing. We end up with a sort of amorphous zone of higher amplitudes in here, which don't quite, you know, they don't really close into any particular fault. So they don't close along strike. So we had two different models for this. One of them was that, you know, maybe there were stratigraphic edges here, and that the trap in this area was actually this size. Or there's an alternative model that maybe all we've got are little blips of amplitude in there. I think if you tab down, those two models are shown. So this is the higher risk but larger model through here. Tab down one more time. The low risk but really too small to be economic model. There's lots of thin fault slivers. And my guess, this hasn't been drilled, so we don't know the result. But again, if you look at this area, there's a lot of recent tilt on this structure. It goes off the top of the section here. But this whole structure has been tilted fairly recently. And that, combined with the fact that the brightest anomalies here really are in these little crestal portions. These are much brighter than the background level. That gets hard to explain. If the real accumulation is like this, it gets hard to explain why you should have these local brighter spots up close to the faults. So what I think we've got again is potentially a broader residual anomaly. Maybe the trap was bigger prior to the recent tilting, but it's been tilted and the gas has leaked around the edges of some of these faults, just leaving you these small accumulations up against the faults in there. So the most likely interpretation is just that we have these small traps, and that the broader amplitude anomaly through here is a paleo feature which got destroyed when this area was tilted. So if you keep going down, this is another area close to one of our producing fields. And so the producing field is in here, and then outboard from that there are some very nice extensive amplitude anomalies, long slender amplitude anomalies in the crest of fault blocks, which look potentially very attractive. So we had a detailed look at this area. We were trying to evaluate whether there was pay which could actually be booked to the field in some of these adjacent slices here. But the problem is the warning signs are that these didn't quite conform with structure. You may be able to see just faintly that the contours cross-cut the edge of the anomaly here. They run parallel to it, more or less, but do cross-cut it in some places. It's sort of it's sub-parallel to structure rather than being completely parallel. Now, sometimes what you do is say, well, actually, this looks so much like a DHI, it must be flat. And there's probably, you know, maybe some slight velocity variation through here. By having a slight velocity gradient, we could easily flatten this on structure. So the question is this a velocity problem, or is it our old friend residual gas that's causing the problem? If you tab down, I think the next few slides demonstrate that this is, again, a residual gas problem. And one of the clues is, again, there's some recent tilting, gentle tilting in this area. So if we pick some of those shallow events and just flatten on them, as we've done previously, then we can see what it does to the anomalies. So the anomalies we're looking at are down in this part of the section here. And if you tab down, there's a detailed view of the anomaly after it's been flattened on that yellow horizon. So these anomalies now, you know, if you flatten on the yellow horizon, the anomalies become very flat. So they are, you know, conforming with that paleostructure, with the structural situation at that time. If you tab down, this horizontal event here, I think, is the paleo contact at the level of our amplitude anomaly. If you remove that flattening, if you tab down again, this is what it looks like without any flattening on. Tab down one more time. I think what we can do is we can distinguish a lightly present-day contact in there. And the brightest amplitudes are actually above that present-day contact. They do, you know, they're still bright down here, but not quite as bright as up at that present-day contact. So this would correspond with the present-day spill point on the structure. This anomaly up here, it's also brightest at the present-day structural closure. So these long amplitude anomalies are almost certainly a sort of paleo response. That again, the story is the same as before. Early charge, probably biogenic, because it is so early when in these features. Early charge before the things were tilted, more extensive amplitude anomalies, things get tilted and you're left with a smaller crestal accumulation, but with a long residual tail. So if you tap down one more time, so in a map sense, rather than this being the extent of our accumulation, the present day accumulation is more likely to just be the extreme crestal portion. So it's tilted towards the north. You can almost take this as still being the current spill point, and draw your accumulation from that point. This is the, if you like, the highest structural point on the amplitude anomaly, and that probably indicates the present day contact. So down one more. We're getting towards the end, but still some juicy anomalies here. This is the one that we were just looking at, TQ65H. Near the top of the quaternary. If you look at the wells that have been drilled in this area on the field, look at the log responses, you'll find that there are, you know, a whole cluster of amplitude anomalies, and the ones that have come in, the ones with pay, are only in the extreme crestal portions. So I've highlighted those with these red blobs here. So other wells, you know, they look at this well that goes down here, didn't actually test our anomaly, but went on down, penetrated this amplitude anomaly, was water wet. Penetrated the edge of this one, that was water wet. An adjacent well down through here hit this anomaly at the extreme crestal portion and found gas, found hydrocarbons. Over here we have a well which went down again close to the crestal portion of this fault block, found pay at these levels, but in the next fault block over, a well going down through a whole series of nice bright amplitude anomalies just found water wet sands. Just residual gas through there. Again, it's down dip from the crest. So this whole area seems to have been tilted. What we're left with are hydrocarbon accumulations at the extreme crests of the fault blocks. But what you're seeing on the seismic data is a paleo response. You're seeing much bigger amplitude anomalies which reflect a time pre-tilting of this area when the traps were a lot bigger. If only we could have been here in TQ65 times. Anyway, if you keep going down, this is just a bigger picture of the same area. We were looking in more detail at this area, but if you zoom out, you see that this whole area is plagued with residual hydrocarbon anomalies. All these blue arrows are pointing at zones, bright amplitude zones, where there's just residual amplitudes. And this is where I kicked myself, because this should say residual up here, it shouldn't say fizz. I meant to edit it, but I just didn't get around to it. So these are all residual anomalies. The red arrows are pointing at amplitude anomalies which actually have pay. Now it's purely empirical here, it's not quantitative, but you will notice that the shallow ones are sort of overwhelmingly blue, but as you go down deeper, there are more red arrows starting to appear. So again, it comes back to these residual gas anomalies just seeming to be more prevalent in the shallow part of the section. So from those observations, I think it's possible to put together some suggestions as to the probable life cycle of residual gas anomalies in the Columbus Basin. The reservoirs and seals, as we all know, in this sort of deltaic setting, they're deposited as horizontal sheets. The initial burial and deformation of those will produce broad, low-relief traps. When you start to deform these things, they're going to start broad and gentle to start off with and get steeper and tighter as time goes on. So those broad, low-relief traps will often have wide catchment areas. Because they're broad, they will be able to accumulate residual gas from wide, well, not residual gas, they'll be able to accumulate biogenic gas from wide areas and potentially produce very broad but thin accumulations. So the biogenic gas will migrate into the traps, form a broad accumulation, but then continued deformation over time will cause that structure to spill and or leak. It's unlikely that you'll preserve these nice broad accumulations over long periods of time in a basin that's as active and as tectonically complicated as the Columbus Basin. These things will get tilted, they will get buried, they'll get faulted, they'll get deformed, and that gas will leak. It will move. So the gas will move away from where it originally was, but residual zones will be left behind as a record of the previous location and previous extent of those paleo accumulations. So that will leave you with these residual anomalies. But then the final point here, this might be a bit more contentious, but I think the reason, if it was as simple as that, we would expect to see them throughout the section. You'd expect them to be just as common in the deep part of the section as in the shallow. But something is actually causing them to not to be present in the deeper part of the section. And I think that's probably because these things do begin to heal or really re-equilibrate over geological time. They seem to be patchier. The residual anomalies, like in that last example we saw, they're not as bright down dip as the present day anomalies are up dip on the crest. But we've seen that the residual saturation should actually give a very similar response. So I think what's happening is that the saturations are becoming more patchy over time. As other hydrocarbons migrate through, then those hydrocarbons will tend to scavenge the residual gas. As the hydrocarbons migrate through the area, they'll tend to pick up these residual gas bubbles, and they will be scavenged and will tend to re-migrate towards the crest of the prospect. Another way that they can decay over time is as you bury these things more deeply, the gas bubbles will compress and will get smaller within the pores of the rocks, and they may then be able to migrate through pore throats which previously kept them trapped. So the gas may become remobilized as the rocks get buried more deeply. And DHIs. We're so convinced that something is a fluid contact that we want it to be flat, and that we think actually the velocities are distorting the picture. So we go in and overrule the velocities and actually flatten these things. Sometimes it's valid to do that, but other times you're going to land yourself in trouble. There may be a powerful message hidden in the fact that it's not conforming with structure. So if there's no obvious geological reason to do so, you shouldn't really adjust the velocities and flatten these things. The residual anomalies, as we've seen, may conform to paleostructure prior to recent tilting and folding. And what I've suggested is that you can experiment with just simple flattening. Just take some of the shallower horizons and flatten on those, see whether you get a better conformance with structure once you've done that. If you do, then that's a clear warning sign. Just a few more on the next slide. Okay, other characteristics of residual gas anomalies, that they may require special pleading for the trap. In other words, the trap might not quite work. Something doesn't look right. The reason it doesn't look right is it's residual. The trap has gone. It's been tilted or faulted. It's no longer there. But you've got to be aware of making special pleading, concocting traps around your anomalies. The residual anomalies may imply unrealistic seal capacities. Check that the geological model makes sense. They may show signs of healing or re-equilibration. The anomaly may have holes in it or ragged edges. Unfortunately, so do a lot of pay anomalies as well. But if you have a good anomaly up dip, nice bright anomaly up dip, but a ragged one down dip, then you've got to ask yourself why one is continuous and the other one isn't. Maybe the down dip anomaly is a residual one. And the residual anomalies may extend down dips from genuine accumulations. So don't completely ignore the anomaly. Maybe the up dip portion of it is actually a valid accumulation. And when you actually get gas, residual gas and water all present, the biggest contrast will be between the residual gas and the water. But the brightest and most continuous amplitudes will probably be from the gas P. So that's the crestal portions of the anomaly. You may have the brightest, most continuous amplitudes. Then you may go down gradually from that without much of a contrast into the residual zone, which has got more ragged amplitudes. And then you may have a big contrast between that and the water-wet zone. So that's about all I have for you. It's just some observations from working the Columbus Basin and from taking an active interest in the residual gas anomalies. If you have any questions, feel free to fire away. Thank you. Yeah, definitely. It may be, with residual anomalies, it may be that the best bits of the reservoir, the most porous bits, the bits where you tend to get the holes in the amplitude anomaly forming first, maybe the most porous, most permeable bits that have the lowest remaining gas saturations, which tend to re-equilibrate. So you could have that response. And also, maybe if the reservoir distribution is patchy, it can obviously also have quite a big overriding amplitude response that you're looking at. So, yeah.
Do you try and demass the seismic by processing it that way, and also increase that collision?
Is not all standard.
What you mean, try to produce density volumes from it, yeah. Or just?
It's difficult, but if you've got good quality together, you should be able to do it.
Yeah, you can. If you had to get my backup slide here, there always will be, for any given shape of anomaly, AVO or just conventional sort of standard anomaly, there's probably going to be some combination of porosity and water-wet sands, which will match lower porosity and hydrocarbon-bearing sands. So, I mean, we do experiment. We do look at the AVO gathers. We do look at AVO cross plots to try to distinguish things. But I think I'm not sure that any of those technologies actually advance us that much beyond looking at the conventional stack response and looking for fluid contacts on that and then interpreting the results. I don't think the AVO response is actually lending that much more to it. I don't know if maybe some of my colleagues will just step in. If you disagree, by all means say so. But I think we're still very much, the most diagnostic features are conformance with structure and flat spots, and you can be tripped up by residual gas anomalies, but looking at the AVO aspects doesn't tend to help you lower the risks really that much beyond where we are.
Can you just show
Okay. An example of an AVO response from this is half-space model shale over sand. It's an AVO responses from different gas saturations and different porosities. So this is a brine response for a top sand reflection, 30% porosity, showing negative gate and an increase in amplitude of offset, because the amplitude is getting more negative with offset. This is a residual gas anomaly, 80% water saturation, 20% gas saturation through here. These bottom two curves here are the ones I want to draw your attention to. So this is the red curve is 80% gas saturation, so it's effectively a fully saturated gas sand, 24.6% porosity. And the darker curve, the sort of greenish, blackish curve here, is only 20% gas saturation, but 32% porosity. the two are virtually indistinguishable. You add a little bit of noise to it, and you can't really distinguish those two. So although there are companies out there marketing products which are based upon third order terms and the Zoebrug's equations, trying to distinguish between low saturation gas and higher saturation gas. Really, the physics is a major obstacle. If you're in a situation where your porosities are constant, then you'd be able to tell low from high saturation gas. But the geology isn't that kind to us. The porosities are varying, and you always will, given some uncertainty of the porosities, I think you have a non-unique solution. There always will be situations where you can get residual gas giving the same sort of response